is the foundation of those other examples. So I hope I've got your attention on this. Okay, suppose now we want to, let's take the event such that order of things does matter. Let's first look at that again as we remember what we've done in the previous section. This is the permutation of things, right? Remember that? So let's look at an example of that. So suppose we have 3 cards, and let's say these are the 3 cards that are these. We have a diamond, a heart, and a spade. Right? Just 3 cards. Okay, so this is the case of permutation, and because we're told that order matters. So order matters, that means we're counting the permutation of events, right? This is different than the combination, which is the main topic in this section. Okay, we learned how to calculate this in the previous section. Let's do it for this problem. So, and this is just an example. So we have 3 cards, 1, 2, 3. And how many cards can we choose for this position? Since order matters, right? We have 3 cards to choose from for this position. And once we select that one card, we have 2 cards left for this position, and then 1 card left for this position, right? And then by the multiplication principle, we can multiply these together, and we've got 6 possible or 6 different ways of arranging these 3 cards such that order matters. So this is a small sample space. So let's list this. So let's listing the sample space, let's just draw it like a diagram. So we have, we should have, or we would expect to have 6 possible ways of arranging these, right? So let me call this number 1, number 2, 3, 4, 5, and 6. Okay, one way would be to pick the diamond card here, and to pick the heart card here, and to pick spade here. That's one possible way. Okay, another possible way would be if we kept the diamond card here, but swapped the spot between the spade and the heart. So if we did that, that would be a second permutation. A third permutation would be if we replace the first spot with the heart card, put the diamond in the middle, and the spade last, right? And that's the third permutation. The fourth permutation would be keep the heart card here, put the spade here, and put the diamond in the last spot, right? And the fifth permutation would be if we took the spade card and placed it here. So let's do that. So spade, diamond, heart, and finally the last spot, or the last permutation, would be I'm sure you can see it, a spade, and then swap the spot between these two cards, heart and diamond. So these are all the 6 possibilities for permutations of 3 cards. All right, so the sample space would be, if we list them, we will have DHS, right? DSH, HDS, HSD, SDH, and SHD. All right, 6 possibilities. Now imagine if we change this problem a little bit, well, not a little bit, but quite a bit, and said that order doesn't matter. So let's do that. Let's add, well, if this is part A, let's make this part B and ask, if order does not matter. Okay, so this very basic example, again, it's important because if you follow this, you follow all the rest of what we do in this section. Very, very important example. Okay, so since the order doesn't matter here, then for this scenario, we're using combination events or combination of events. Okay, think about it. Before I write down the answer, think about how many different possibilities are there with these 3 cards if the order doesn't matter. Think about it for a few seconds, or pause the video before you see my answer. Well, if order of these cards doesn't matter, then there is only one way to hold these cards. This is, I call it, for a lack of a better term, the gambler's perspective. So if a gambler had these 3 cards in his or her hand, how many arrangements does he think he or she have? Well, just one. It's the same set of cards, right? So just one. There is only just one, right? Just one possibility of arranging these cards if order of these cards does not matter. Well, now, how can we get to this answer numerically? Well, okay, so we have the original 6. So we had, let me write this down again, 3, 2, 1. This is what we had for the permutation, and we multiplied these. Now, take a look at how many positions you're filling with these 3 cards, right? Now, it doesn't matter if the original items from which you were selecting were 5 or 10, but the positions for which you're selecting, there's just 3. So, if you discount the order, then you have a lot of duplicates in here, right? You have a lot of duplicates because it's the same set of cards arranged differently, but order doesn't matter. So there are 5 duplicates of one arrangement. How to get rid of that is simply divide this number, which represents the permutation, by how many spots you were choosing for. So in this case, 3. So we have 3 spots, factorial. This, whenever you do this to a permutation, it'll get rid of the duplicates, and it'll give you the number for combination such that order of things does not matter. Okay, so if we do that, this will be 6 over 6, which of course is 1, which we know is the true answer for this example. It's always like this. So figure out how many spots you have that you're picking for, divide the permutation number by that number of positions you're filling for, factorial, like in this case. This is just a way of reasoning for it. Of course, calculators have buttons that will give you the combination, regardless of if you are able to reason for this numerical calculation or not. So you can just calculate with your calculator and not knowing what's the reason, what the reason is behind that number you get. But this is the reason behind it. And we will talk about, and actually I should talk about that right here. Maybe I can, let's see. So we can do that here, I guess. All right, suppose we want to, using this TI-30X calculator, we want to see how many combinations are there for 3 objects, right? Such that order does not matter. So you enter 3. Then on this calculator, the PRB is for probability. You press that. The first one, NPR, last time we discussed this, that's permutation, right? That's when order matters. We don't want that. So we scroll over, we use the arrow key to scroll over to NCR, which is combination of events. So I'm going to pick that by pressing the enter button. So the calculator picks it, but it's not running it yet. So 3 combination 3, right? In how many ways we have 3 objects, or cards in this case, in how many ways we can arrange this such that order does not matter. 1. Okay, which is the result we got. But now you know why we get that 1, because we're dividing by 3 factorial, which is the number of positions we're selecting for, and this number, what this does, it gets rid of the duplicates in there. Okay, so the other thing we should talk about is, we talked about this when we discussed permutation, is the notation for combination. You should know this. I'm not so picky about this, or probably you won't need it for the exam, but in case you read different books and you see authors use the notation differently, I think you should be familiar with that. So let me just briefly mention that as a note. So if you see a notation like this, a capital C parentheses N comma R, that's the same thing as this notation. A capital C with lowercase n in this corner and lowercase r in this corner, and that's also equivalent to this notation. Okay, so all of this, this refers to choosing I should say a smaller group of R objects or things from a larger group of N objects or things such that order of selection or arrangement does not matter. Okay. And the C stands for combination. Let me put in parentheses, i.e. combination of events. Like that. Okay, so let's see more examples. Every time I work out an example, if you don't follow what's happening, please go back to this original example, this one that we just discussed. This simple example is the backbone of all those other more complicated examples. Okay, suppose we're asked to find from a pool of 7 students. Okay, you've served, probably, most of you have served on student committees, right? So this is a problem that says, in how many ways can a committee of 4 students be formed from a pool of 7 students? Well, this is the scenario that we just talked about, which is the combination case, because we're selecting a smaller group of 4 from a group of 7, and they're going to be on a committee. On a committee, the ordering does not matter, right? I mean, if it does matter, then the problem would have to make that more explicit. For example, a committee might be comprised of a president, a vice president, a treasurer, and a secretary. Then in that case, if we are given clues that there is some kind of ranking involved in the membership of the committee members, then yes, order matters. But here, the problem is not telling us whether order matters or not. From the context, we gather that there is no ranking or ordering of the committee members. So order does not matter. That's the first thing you want to establish when you see a problem like this. So from the context, we can derive that order does not matter. Okay, so as soon as we establish that, then we know we have to calculate combination, a combination value. Okay, so we can do that. I'll show you both the method that shows more reasoning and with the calculator which just calculates the number. So we're selecting for 4 spots, right? So 1, 2, 3, 4. And we're selecting from a group of 7 people. So how many people are there to choose from for this position, for this spot on the committee? 7. Once we pick a person for that, there are 6 more people left for the second spot, and then 5 more people for the third, and then 4 more people left for the fourth spot. Okay, so if we multiply this by the multiplication principle, the number we will get is the permutation when order does matter, but we don't want that. We want to get rid of all the duplicates because people were arranged, the same people were arranged differently. But that's not going to change the committee, right? It's still the same committee because these are the same people. Putting them in different spots or seats, it doesn't matter. So to get rid of the duplicates, then we want to divide this by the number of positions that we're selecting for factorial. So 4 factorial. Okay, so if we calculate this, we will get 840 divided by 24, which is 4 factorial, equals 35 possible ways of picking committees that have at least one member different than the other committee. Okay. All right, so let's calculate this with our calculator. This on a calculator, this would be 7 choose 4, right? So let me write that down. On a calculator, this would be 7 choose 4. All right. So I'm going to enter 7 first. Then I'm going to hit the PRB button. I don't want permutation. I want to pick combination. I'm going to hit the enter button to select combination of events. And we're picking 4 out of the 7. So 4, and then press the enter key. And you get 35. So that's another way of calculating combination of events. Okay, so let's see another example. Okay, given this scenario, we're asked that and 3 diamonds. Okay, so we have a larger set of cards from which we want to pick a smaller set of cards. But nowhere in this problem they indicate that order of selecting these cards matters. So because they don't have any clue here about that, then we assume that order does not matter. So from the context, order does not matter, so use combination. So on an exam, problems of this type are mixed with problems of the permutation type. So you have to pay particular attention to whether order matters or not. That's the first thing you want to establish before you pick your methodology for solving the problem. Okay, so knowing that, then let's organize this information. Bring this down. So we have 14 cards total, 3 are spades. We have 3 spades. I'm just going to put an S there. And 7 are hearts. And 4 are diamonds. All right, that's the total, 11 and 14. In how many different ways can we select 2 spades? Okay, so that would be 2 spades from the spades group, 4 from the hearts group and 3 from the diamonds group. Okay, now we can scroll up because we have captured all that information. We've already established we have to use combination, so then 3 choose 2, so that would be 2 spots. Just 2 spots. We're picking for 2 spots. And these are the spades, right? So we have 3 cards to choose from for 2 spots. So we will have 3 options for this spot and then 2 options for this spot, right? So we can multiply these by the multiplication principle, but if I left it like this, this would count the permutation of these 2 cards, not combination. What do we have to do to get rid of the duplicates? You guessed it. We have to divide by the number of positions factorial. So 2 factorial. That will get rid of the duplicates in there. Okay, so now for the hearts group, we're picking for 4 spots. So 1, 2, 3, 4. Right? This is for the hearts group. And we're picking from 7 cards. So 7, 6, 5, and 4. By the multiplication principle, we can multiply these. And if I left it like this, this would count the permutation of these 4 cards. So we want combination. To get rid of the duplicates, we divide this group by the number of positions factorial. So this would be divided by 4 factorial. Okay, for the diamond group, we're picking for 3 spots from 4, so 1, 2, 3. And this is the diamond group. And so we have 4 cards to choose from. 4 options exist for picking for this spot. Then once we pick that card, then there are 3 options to choose from for this spot, and then there are 2 options left for this spot. So multiplying these by the multiplication principle, you don't want to leave it like this because this is not permutation. Order does not matter here. So we want to get rid of the duplicates. So divide this number by the number of spots factorial. So this would be 3 factorial. Okay, so here then for this number we have 3. And of course these are being multiplied by the multiplication principle. So 3 times this one is 35, and then multiplied by 4, and then multiply all of these, you get 420 as total possible different ways we can pick these many cards from these groups. That many possibilities exist. And I trust if you have any questions about this, you'll bring it up either during the WebEx sessions or or you post your comment on the discussion board. Okay, so this was part A. For part B, we want to find the probability of this. So what's the probability that we select these 9 cards from a group of 14, and we have 2 spades, 7 hearts, and 3 diamonds? Okay, the probability of that. So what is Okay, so this 420 is the number of desired outcomes, right? To find the probability of this, we need to divide that by the number of total possible random outcomes. In other words, these 14 cards that we started with, we picked 9 cards from 14, right? But we're doing this randomly. So how many possible ways are there to pick 9 of these cards from the stack of 14 cards. We need to find what that number is, because once we have that number, we can divide this 420 by that, and we have probability of these desired outcomes. Okay? So, picking 9 from a set of 14, this is 14 choose 9. I'll show you again both ways, with calculator and with this method that you just saw in this part A of this example. So let's first go over this part. So we want to know the total possible ways of selecting 9 from 14, right? Or 14 choose 9. It doesn't matter which language you use, this one or this one, they are the same thing. Okay, usually authors in their books, they use this language for referring to a combination event calculation, 14 choose 9 in this case. Okay, so that's pretty easy because we have 9 spots to fill. So let's draw that. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have 14 cards to choose from. So we have 14, 13, 12, 11, 10, 9, 8, 7, 6. If you left it like this, you're counting permutation. So please don't forget that. For combination events, you do not want to leave it like that. You want to divide this by number of positions that you're filling factorial. So 9 factorial. And that'll give us the number of combination events. All right, so then what I got was this large number in the numerator. Like that. So 726,485,760 divided by 9 factorial, which is 362,880. So what do you get? You get 2002. But that's just all possible outcomes. It's not the probability. It's not the probability that we were calculating, right? So I'm running out of room here. Let me move to a new page. So we had the desired number of outcomes. So the desired number of outcomes. This is the 420, right? Which contains 2 spades, 4 hearts, and 3 diamonds. That's the desired outcome. So we have that. And then we also counted here total possible ways of selecting 9 from 14 cards. And that's 2002. So to find the probability, we simply take 420 divided by 2002. And what I got was 0.2098, which is carried to 4 decimal places. Okay, so let's look at another example. Okay, so here we have a committee that is being formed, and there is no indication in this problem statement that ranking of these people matters. Again, if you have a committee that is talking about people that are ranked, like the president, the vice president, the treasury secretary, that is a clue to you that order matters. So that would be a permutation calculation, but not here. So definitely, is my microphone fell off. That. Okay, so first thing we want to establish is that from the context, does not matter, therefore use combination. Okay, so from these, from these 9 people, let's draw some kind of a diagram to make this a little bit more organized than it is. So we have 9 people, and this is being used to form committees of 4, then 3, and then 2 people. How many different committees can be formed? Okay, so we have, let's form this committee first. There is more to this problem actually, I didn't see. Let me put that. So for part A, we want to know how this could happen if a person can serve on any number of committees. Academic committees are most of them, I can't think of an exception, academic committees are always like this. So you can serve on multiple committees, on the personnel committee, on the curriculum committee, on the judicial committee, and accreditation committee, and so on and so forth. So for that reason, once a person is picked for one committee, that person is free to serve on any of the other committees. So for this committee, it would be 4 spots to fill. For this committee, it would be 3 spots to fill. And then for the last one, just 2 spots to fill. All right? Okay, so let me make this clear by saying this is the committee of 4 people. Committee of 4. This is the committee of 3. And this is a committee, this is the committee of 2 people. Okay, we have the original 9 people. So there are 9 people to choose from for this spot, then 8, then 7, then 6. By the multiplication principle, we multiply these. You do not want to leave it like this because this is counting the permutation. So divided by the number of positions you filled, factorial. So divide by 4 factorial. Let me make that blue so it stands out with respect to this. So these people are free to serve on this committee. So once again, we have 9 people to choose that spot, and then 8, and then 7. So again, we multiply these by the multiplication principle. Don't leave it like that. Divide that by the number of positions you're filling, factorial. So 3 factorial. That's 2 spots to fill. Again, these people can serve there. So 9 and then 8, multiply them, divide by the number of positions you're filling, factorial. And of course, all of these outcomes for each individual committee are being multiplied by each other by the multiplication principle. So I'm sure by now you're seeing that the multiplication principle is everywhere. Okay, now let's, I have calculated one final number for this. So after you figure out this number, and that, you should obtain 381,024 different possibilities exist for this. Let's change this part A to finding the number of committees if no person can serve on more than one committee, right? So you might want to pause the video and come up with the solution for that before you look at my solution. So for part B, or I should say if no person is allowed to serve on more than one committee, are formed first. So no person is allowed to serve on more than one committee, and the committee that has 4 people is formed first. Then the committee that has 3 people is formed second, and finally the committee that has 2 people in it. Okay, I'm counting on that you've already have your solution and you want to look at my solution here. Okay, so we have 1, 2, 3, 4, and we have 9, 8, 7, 6. By the multiplication principle, we multiply these. We cannot leave this like this because this would count the permutation. We want to get rid of the duplicates, just like that first example that I showed you with the 3 cards. And this is the same justification. Divide by 4 factorial. All right, so the next committee has 3 people in it, but this time these 4 people who were picked for here for this committee cannot serve there. So we have only 5 people to start with. So 5, 4, and 3. We're filling 3 spots with these 3 out of 5 people. To get rid of the duplicates, divide by 3 factorial, and finally, for the group that has or the committee that has 2 people in it, we have 2 people left and 2 spots. So this would be 2, 1. Multiply that, divide by 2 factorial, which will give you 1, which it should, right? In how many ways you can fill a committee of 2 people with 2 people? Just 1, right? And order doesn't matter. Okay, so after that, I got, these are the numbers I got for this one. I have 126 times 10 times 1, right? And that's equal to 1,260. Okay, so let's see more examples here. I want to start on a new page because then I'm going to run out of space here again, so it's better that way. Random, and let's see. Okay, so given this scenario, okay, so we have in a lottery 48 balls numbered 1 through 48 are placed in a machine. We've seen those, right? The round big machines. And 6 numbers are drawn at random. So if the 6 numbers drawn match the numbers that a player had chosen, the player wins $1 million. What is the probability of winning the prize if the order of numbers on the ticket does matter? So that's the assumption that they make for part A. Great, so they are telling us assume that order matters. That's all we need, because then we know that for this it's the permutation that we need to use. So use permutation calculation. All right, we know exactly how that works. So this would be I'll show you both using the calculator and the reasoning method. So with the reasoning method, we're filling 6 spots. So 1, 2, 3, 4, 5, 6. And order does matter. So we have 48 to choose from for this spot. Once that spot is out, then we have 47 to choose from. Then 46, then 45, 44, and 43. And of course, by the multiplication principle, we multiply these together, right? And then divide these, so this is for permutation. So this number I got, it's a very large number. So it's 8 billion, right? 8,835,488,640. Okay, possibilities. Okay, so now this is the count. Now, I know in actual lottery tickets, there are various winning tickets, tickets that win $250,000, tickets that win 1,000, tickets that win $50 or $2. But here we're assuming that there's just one ticket that is going to win anything at all, and that one ticket is worth $1 million. And we want to know the probability of that. So in this case, then we simply take 1 out of that. So divide, let me write that assuming there is only one winning ticket, then this is how the probability of it is calculated. So we have 1 over all of that. $40, and that is equal to a very small number. Like that, 113. So that's one way of giving the answer. Another way is giving this answer using the scientific notation. So notation, you can write this down as 1.13 times 10 to the negative 10. So it's just saying that what this means with the negative power is that move this decimal 10 spaces to the left and you get that same number. So this is scientific notation, that's the decimal value notation. Okay, so now let's do this, calculate the same number, but if the order of numbers on the ticket does not matter. So as long as the participant gets the same numbers in any order, he or she will win. Okay, so that would be part B. Right off the bat, something occurred to me. Right off the bat, you know that this number has to be larger than that. The reason is permutation is always a larger number than the combination. Just think back to that first example we did at the beginning of this section with the 3 cards. Permutation had 6 possible different ways of ordering the cards, right? But the combination of the same set of cards had only one event. So going from 6 to 1. And the same thing here. Because the number of possible events is going to be much less than this, so the probability of winning for combination will be higher. Okay, so okay, so this is the hopefully I can fit all the rest of the solution here at the bottom. So use combination, and then this would be 48 just like before, 47, 46, 45, 44 times 43. Divide all of that by, since this is order does not matter, divide by the number of positions, which is 6 factorial, right? 6 factorial, we will get this number, 1 million or 12 million. 12,271,512 possibilities. Now, to find the probability, we would say 1 divided by that number. 12, which is this number. So 3, 6, and 7, 8, 1, 5, either this number or 8.15 times 10 to the negative 8, like that. Oops, like that. Okay, so that's another example. Let's do another example. Okay, so we have a small search party of 8 individuals is to be selected at random from 8 women and 11 men volunteers to look for a group of missing hikers. So let's organize this information. We have a total 19 volunteers, right? And out of these 19 volunteers, we have 8 women and we have 11 men to look for a group of missing hikers. In how many ways the search party can consist of 3 women and 5 men? Okay, so you got to be thinking about, does order matter in this case or not? And right away you can tell order does not matter, right? It's just the same search party. Does not matter in which way we pick the people that are going to be on this search party. So establishing that, we know that order does not matter. So use combination. Okay. Knowing that, then we're counting in how many ways this 8 people can be put together given this group of volunteers. All right, since we know order does not matter, then we have 8 choose 3 and then 11 choose 5. Okay, so we have 1, 2, 3. This is for the women group. And then for the men group, we have 1, 2, 3, 4, 5. By the way, I forgot to discuss in the previous example the calculator way of calculating those numbers. I'll go back to it and we'll talk about it. And then with the men group, so 8 choose 3, so we have 8 people to choose from for this spot, then 7, then 6 for the women's group, and then of course they get multiplied by the multiplication principle. We do not want to leave this like that because this is going to be permutation. To get rid of the duplicate arrangements, divide by the number of positions we're selecting for factorial. Same here, we have 11 people from which we're picking 5, so 11, 10, 9, 8, and 7. Multiply these, get rid of the duplicates by dividing by the number of positions factorial, so 5 factorial. And of course, these two results get multiplied by each other. So we end up with 56 times 462 equals 25,872 possible ways of forming this group of 8 people on this search party. Okay, so let me, I guess we can go back to that lottery problem. We are picking for the permutation part. We want to, let me put this so you can see it hopefully. So we had 48 balls from which we chose 6. If order does not matter, or if order matters, so that's the permutation, right? 48 PRB. The first one is the permutation, NPR. Let's hit enter to pick that, and 6 balls coming from that, so that'll be that number that I have there, right? Same number, you see that right there. Okay, so for combination 48 choose 6, which is the scenario we had here for part B of the previous problem. Let's calculate that. So we have 48 and PRB again. This time we want combination NCR. So scroll over to that option, hit the enter key to pick it, and then enter 6. So that's 48 choose 6, which is when order does not matter for part B. And we have that number, which is right there. Okay. All right, so this is just showing you the calculator way of coming up with those numbers, whereas what I'm showing you is the reason why we have these numbers. Okay, so for part B of the same problem, they're asking for the probability of this, what we got here. So what is three women and 5 men. You know, I could have asked this question from the start. I mean, but you still would have to go through part A. I hope you can see that, right? So if there was no part A for this problem, if I went and said, given this data, what is the probability that the search party consists of 3 women and 5 men, you would have to calculate this 25,872 anyway. But I'm breaking it up into 2 pieces so you can see the different components. But if we went directly to this question, you'd have to figure this out, because this is the number of possible ways of a desired outcome, which has 3 women and 5 men from this group of volunteers. And then we could calculate the probability by figuring out the total possible ways that these 8 people can be picked. So all possible ways of 19 choose 8. That's what we need to calculate. Once we have this number, then we will divide this number by this number and we calculate the probability of that outcome. But this is all possible ways of that 8 can be chosen from 19 randomly. Okay, so this would be the reasoning way would be 8 spots to fill, right? 3, 4, 5, 6, 7, 8, 18, 17, 16, 15, 14, 13, 12. Multiply all of these together. You don't want the duplicates. This is order does not matter. So divide by the number of positions factorial, 8 factorial. And you should get, what is that number? Did I calculate that or not? Yes, I did. So this number is 75,582. Once you have that, then you can divide that one by this number. So 25,872 divided by 75,582, and we get 0.342, which is the probability carried over to 3 decimal places. Okay, so let's do one more example, and then we can wrap up this section. Placed and add 4, 7, Okay, so we have a small airline company has purchased a new jumbo jet and has placed an ad for hiring 7 experienced flight attendants. The company receives 9 applications from male and 7 female applicants. So we have a total of 16 applicants, right? 16 total applicants. And out of these 16, I'm just organizing the information in this word problem like we've discussed earlier during the semester. So from the 16, so 9 are male and 7 are females or women, and assuming that all applicants are equally qualified, what is the probability that 3 male, okay, so we need to then show that as well. So from 3 male, from this group of 9 male, 3 is chosen, and 4 female from the 7, 4 are hired to be on this crew. Okay, so again, if you see this as part of an exam, you have to establish whether order matters or not, because permutation problems and combination problems will be mixed on an exam. So that's the first thing we want to think about. And from the context, there is no order that is not important at all, right? On an airplane, the crew, in terms of gender, it doesn't matter. But in terms of their ranking, whether they have a higher rank or more seniority, all of that exists in the real world, but in the context of this problem, we're not considering those. Okay, so just looking at the information we have, order does not matter. Order of hiring does not matter, so that means use combination. Okay, so that would be 9 choose 3 and 7 choose 4. All right. To be on plan. So, so they're asking, yeah, this problem is directly jumping to probability calculation. So it doesn't break the problem up into 2 parts like the previous problem where it has parts A and B. So directly, it's giving you the scenario and what's the probability. Great. So, but just like the previous problem, we have to break it up into 2 pieces. One, calculate the number of desired outcomes, which is 3 male and 4 female ones, and then calculate all possible ways that you can pick 7 people out of 16. All possible ways. And then divide the number of desired outcomes by the total number of possible ways of selecting these people from the larger group, and you get the probability that you're looking for. So let's first calculate the number of desired outcomes. So that would be 9 choose 3 times 7 choose 4. So you can pause the video actually. It would be a really good idea to pause the video, finish this problem on your own, and then come back to my solution. I'm assuming you've done that. And now you're back and you want to see what my solution looks like. Right, so multiply that, and of course this order doesn't matter, so divide by the number of spots you're filling, factorial. Here we have 7 choose 4, so 7, 6, 5, 4. Multiply these together. and then divide by the number of spots you're filling factorial, so 4 factorial. And so what I have for this would be is 84 times the number I have here is 35. So I have 2,940 as the number of desired outcomes. We want the probability of that. Okay, so to do that, we need to figure out how many possible ways we can pick the crew of 7 flight attendants from the total 16 people who sent in their applications. Okay, so like that. So that was the number of possible desired outcomes, and this will be number of possible ways of 16 choose 7. That is what we want to calculate. Well, okay, so once again, we are filling in 7 spots, right? And order doesn't matter, so we divide this whole thing by the number of positions we're filling factorial, so divided by 7 factorial, right? So here we have 16, 15, 14, 13, 12, 11, and 10, like that. And then that number, according to what I have here, so I ended up getting this number for the numerator. So it is 57,657,600 divided by 5,040, and that is 11,440. So here we have the number of desired outcomes, which would be 3 men and 4 women, with no order being important. And here is all possible ways we can select 7 individuals from 16, or 16 choose 7. So to find the probability of this desired outcome, we divide this by this number. And this would be the probability of the desired outcome. So 2,940 divided by 11,440, and we get 0.25699. Why don't I round this to 3 decimal places, like that. Okay, so this wraps up section 8.5. Please remember, you can discuss your questions face-to-face on WebEx during the first 30 minutes of each class, or post your questions right underneath the video on the discussion board. All right, so have a nice day, and see you next time when we cover section 8.6. 8.6 will be the last section we will cover in this course. So see you all later.